All right, so welcome everyone to the OpenSim webinar. I'm pleased to be presenting as part of the European Society of Biomechanics webinar series. Asan, I'm getting some audio from you. So I'm gonna go ahead and hang up the Skype call. Okay. So I'm excited to be speaking to researchers from all around the world to introduce you to OpenSim. If this is your first time learning about it, or if you're already a member of the OpenSim community, I'll show you some of the new features of OpenSim 4.0, which is the latest version of the software. I'll also give you an update on new research happening in the community and some pointers on how to get started with OpenSim and learn more. My name's Jennifer Hicks. I'm the Associate Director of the National Center for Simulation in Rehabilitation Research, which develops and supports the OpenSim software and the OpenSim community. So OpenSim is an open source software package for modeling the musculoskeletal system and simulating movements. OpenSim is used by researchers around the world to study a wide range of movement. So this slide shows a few exciting examples of how OpenSim is being used. So Ravi Balasubramanian of Oregon State University is using the software to model the effects of artificial tendon networks and simulate how they affect hand motion after a tendon transfer. Marjolein van der Kroot from the VU in Amsterdam is using OpenSim to simulate the effects of muscle spasticity. Stefan Verbruggen and colleagues at Imperial College are using the software to simulate fetal kicks in the womb. And Brian Umberger and Frank Supp of the University of Michigan and UMass Amherst are using OpenSim to model the limb socket interface in amputees. So users are pushing the software to new and exciting uses, which necessitates a set of flexible tools for studying movement. We'll learn more about these tools in today's webinar, and I hope you'll be able to apply them in your own research. I'm just gonna check in quickly. Okay, I don't see any comments, so it sounds like you guys are still hearing and seeing the slides okay, so I will keep going. So here's the plan for our presentation this morning. First, I'll talk a little bit more and give some background about what OpenSim is. Then I'll do a live demo showing some of the key features of the software. And hopefully the technical details there go more smoothly than getting the webinar started. And then I'll close by talking about how to learn more and get started. So first, what is OpenSim? So OpenSim is free and open source software for modeling humans and animals and simulating their movement. OpenSim can model many structures, including biological and mechanical systems. So OpenSim has components and tools to emulate neural control. It also has biological joints. So humans are not composed, for example, of all pin joints. And you can model the physiological complexity of real joints. Models can be tuned and scaled to represent individual subjects. And we also provide sensors to estimate things like metabolic energy consumption during movement, we also have models of muscle tendon dynamics and models of ligament and joint contact. And OpenSim can also model non-biological structures like assistive devices and prosthetics. So we've designed OpenSim to be flexible and modular so that others can extend and adapt the software to their own research needs. I see that someone raised a hand or sent a chat. So we'll definitely take questions, and you can type those in the Q&A panel of the Zoom interface, but I'll answer those questions at the end of the webinar. So going back to the presentation, models in OpenSim can be as simple or as complex as you need. So combining just the elements that you want. For example, on the left, the model on the left is a simple hopper model with a block and 2 links. And on the right is a model with 23 degrees of freedom and 92 muscles. And you can query the model or any of its components to understand and compute what you'd like to learn from a simulation. For example, one type of component you can include in a model is muscles. And you can output things like the fiber length or the fiber power, the force multipliers, and many more quantities during a simulation. Joints are another component in OpenSim. From joints, you could compute and output joint reaction forces. These are just a couple of examples of what you can extract from an OpenSim model, and we'll learn more about the OpenSim components and these outputs in the demo a little later. So OpenSim provides a user-friendly GUI or graphical user interface that allows easy access to this underlying functionality. This GUI is now cross-platform, running on both Mac and Windows. In the GUI, you can load and visualize models. There's a suite of tools for importing experimental motion capture data, and then computing things like inverse kinematics, inverse dynamics, and then generating muscle-driven simulations. And we'll see more about this in the demo. You can also develop and share models with OpenSim. For any of you in the audience who've developed your own models, you know that creating a new model is a lot of work. So OpenSim also provides a repository of models, so you don't have to reinvent the wheel when you're starting a new study. So we have an online repository of models, and I'll show just a couple examples here. So Matt Demers, who is a grad student in our lab, created a model with physiologically accurate models of the ankle and stretch reflex controllers to understand the role of reflexes in preventing ankle inversion injury. Kat Steele and others have created models to simulate the crouch gait pattern in children with cerebral palsy. AJ Seth and colleagues created a model of the shoulder with a physiological scapulothoracic joint that's fast and accurate compared to bone pin data. And you can also create animal models. So this ostrich model was developed by Jeff Rankin and colleagues to study locomotion. We carefully test all of our simulations by comparing them to a wealth of experimental data, including joint kinematics, joint moments, ground reaction forces, muscle activation patterns, muscle forces, and joint reaction forces. Verification and validation are vital for any type of simulation, and so we use a suite of tests to ensure we can trust our software and the results of the simulations that we share. We also provide guidelines to the community so that researchers new to modeling and simulation can better understand what verification and validation steps are needed to trust the results of a new study they're performing. OpenSim is a software package, but it's also a community, and this community continues to grow and diversify. The OpenSim community has thousands of users and hundreds of experts around the world. And this map shows visits to our documentation over the last year. So it really shows the worldwide impact we're starting to have. This bar graph shows the publications citing OpenSim organized by research category. Sorry, just checking I saw a question pop up, but again, I'll answer those at the end. So each bar in this bar graph shows the % of publications that come from a given discipline. So we see that OpenSim is used for biomechanics research and also in robotics, computer science, and the neurosciences. OpenSim is enabling interdisciplinary collaboration between biomechanists and all these other fields. This next plot shows, let me bring that up, shows the cumulative number of unique users of OpenSim since its release in 2007. As of yesterday, over 40,000 individuals have downloaded the software. So now let's get started with the demo so that you can see OpenSim in action. I'll use the demo to highlight some of the key features for users who are getting started, and also show a couple of the new things in 4.0. To demo the software, we will generate and analyze a muscle-driven simulation of a vertical jump with a counter movement. So hopefully that video played okay for you. We're using a simplified model with 18 muscles and 10 degrees of freedom. And the video showed a preview of the motion that we'll simulate. So you can see the jumping motion, and you also see the muscles turning from blue to red as the muscles are activated. So here are the topics we'll cover in the demo. We'll become more familiar with OpenSim's graphical user interface. Then we'll analyze motion capture data of a subject jumping, and then do solve for muscle activations that generate a jumping motion, and we'll do some simple analysis of the activations and other quantities that we compute. Before we start with the live demo of the software, I'll give some important background about the overall simulation pipeline and how to go about importing your experimental data into OpenSim. So for many muscle-driven simulations, the simulation pipeline looks something like this. We start with experimental motion capture data of the motion of interest. This data is often in the form of the C3D file. And as of OpenSim 4.0, you can use OpenSim directly to read in the C3D data with marker and ground reaction forces. You can preview this experimental data in the GUI as shown in the image on the right-hand side. But typically everyone's lab and experimental setup is a little bit different, so you'll need to first do some transformations and other cleanup and prep of your data. Many users, researchers and users have MATLAB, so we provide OpenSim capabilities through MATLAB scripting. So on this slide, I'll show some simplified code that demonstrates the process that you use to import your C3D data. So first we read in our data. OpenSim uses something called adapters to help convert from different data file types like C3D or TRC to OpenSim's data file formats. We create an adapter and then read in tables with marker and force data from the C3D file. Then in MATLAB, you can do post-processing, like for example, rotating the lab coordinate system to match the OpenSim's coordinate system, or computing center of pressure. Then you can write your files to TRC and STO files, which the OpenSim tools use, like the OpenSim tools for inverse kinematics and dynamics can use those files to run the analyses. We've already done this pre-processing for the demo today, and we provide example MATLAB utilities with your OpenSim distribution to help you complete this process for your own data. So we've read in our experimental data to get marker positions. These marker positions will be used by OpenSim's inverse kinematics tool to compute joint angles. The joint angles, together with ground reaction forces, are used by the inverse dynamics tool to compute joint moments, and the static optimization tool to compute muscle activations. So this is an overview of the steps we'll perform in the demo, and I'll go into more detail for each as we step through. All right, so let's go ahead and switch over to OpenSim. All right, let me expand OpenSim. So here is the OpenSim graphical user interface. When you first launch the application, you'll see some links to our documentation, including the user's guide and examples. To get going, we need to load a model. So I will load the jumper model that we're going to use in the example. And while that's loading, can someone just confirm for me that they can see that the OpenSim application is showing up okay? Oops, let's see. Okay, looks like we're good. Thank you, guys. Okay, so let's go ahead and continue with the demo. So here's the model that we'll use in the example. You see its skeletal geometry, the simplified set of muscles, the model markers that we'll try to match to the experimental data in the IK step. Note that to save time, I've already scaled this model to match our experimental subject. This is a key phase in the process. And you can see our user guide and past webinars to learn more about how to scale your model. You can use your mouse or trackpad or your keypad as well to zoom in and out and change the view. So can zoom in and out, go up and down. I'll point out the other key components of the application. So again, this is the visualizer window where you can visualize your model or experimental data. Up here, the video controls allow customized playback for a loaded or computed motion. They're grayed out now because we haven't generated or loaded a motion yet. The messages window gives the status of OpenSim's operations. And then over here we have the navigator, which shows your loaded models and the model's components. So for example, we can see the bodies that make up the model, the pelvis, the femur, the joints that connect the bodies. There are no constraints or contact geometry in this model. It does have forces in the form of muscles, our force generating elements. And then again, we have markers in the model as well. The coordinates pane shows the degrees of freedom of the model and their coordinate values and speeds. And then if we select, say, a body in the model, we can go, or any of the other components in the navigator, we can go down to this properties panel, which shows detailed information about a model component, the model component that's selected, as well as the outputs, which we'll learn about a little bit later in the demo. So we want to analyze that jump. So let's go ahead and get started with that. And we'll begin with an inverse kinematics analysis. So kinematics is the study of motion, an object's position, velocity, and acceleration. And in OpenSim, the purpose of inverse kinematics is to find the joint angles of the model that best reproduce the experimental data that we measured for a particular subject in trial. OpenSim determines this best match by solving a weighted least squares optimization problem with the goal of minimizing marker error. In this tutorial, the experimental data used by the IK tool are the experimental marker positions of a subject performing a maximum height jump. And with the results of the kinematics analysis, we'll be able to probe the model in motion for quantities such as jump height and takeoff speed. So I can find the inverse kinematics tool under the set of tools. So I'll go ahead and launch the IK tool. In preparing for the webinar, I saved what's called a setup file, which has all the settings for running IK. So I'll go ahead and load that so I don't make any mistakes during the webinar, and I'll talk through what each of the inputs are. So the model is the jumper model. We have a set of the 44 markers. The marker data is in jumpmarkers.trc. We're going to process from 0.6 to 1.95. And here, the output where we're going to save the motion file is right here, the inverse kinematics solution jumping.mot. And then I said it was a weighted optimization when I was talking about IK, so you can apply different weights to the markers. But in this case, to indicate, for example, how much you trust each value, but in this case, we've set all of the values to 1. But you can adjust those for your own simulations and setup. So I'll go ahead and run inverse kinematics. And we see the model jumping and landing. So we can play that back. It may be a little bit choppy over the webinar format, but hopefully you guys at least get the general sense that we have a simulation of a jump here. We can use the playback to get a sense of the max height. It looks like it's the time that the max occurs. It looks like it's a little bit after 1.6 seconds. We can also plot the joint angles that we computed. So I'm launching from the tool menu, the plotter tool. And for my Y quantity, I can look at those inverse kinematics results. And let's plot the hip flexion and knee flexion and ankle plantar flexion. And our X quantity will be as a function of time. And I'll go ahead and add those curves to the plot. And we see that the joints are flexing during the counter motion, extending during the push off, and then are extended and stay fairly constant during the flight phase. Another question that we might have, so we have these joint angles, but something that isn't directly outputted from the inverse kinematics analysis that looks at joint angles is the position of the hand and the position of the center of mass throughout the jump. But we can use the new output reporter in OpenSim 4.0 to easily compute those things. So I talked about the properties and the outputs earlier in the demo. If we go ahead and look at the model and its outputs, we see that the model has an output called the center of mass position. So we could use that to plot the center of mass position throughout the jump. And then we can look at the outputs of the bodies as well. If I find the hand, let's look at the right hand. We can see that we can also plot the position of the hand over time as an output. So to get those outputs for the motion of interest, I'll use the Analyze tool. So I'll go ahead and load the Analyze tool. Again, I've already created, pre-populated a setup file so we don't miss anything. So I'll go ahead and load that, my output reporter setup for getting positions. The motion is the result of the inverse kinematics that we just ran. We're going to look at the same time range. The results will go to this folder, results position outputs. This is just a kinematics analysis, so we don't have actuators and external loads to worry about. And if we go to the set of analyses, we see that we have this output reporter. And if I edit that, we can see the output paths. So those are kind of like file paths, but paths to different outputs in the model. And we see we have the center of mass position, and then find the body set, the right hand, and the position of the right hand. So if I go ahead and run that, I can close the tool while it's running. It played back really quickly, but we have the same motion. And now if we bring up the plot tool again, we should be able to go ahead and plot the hand and the center of mass position over time and get some information about the jump height. So here's the folder that I used, results, position, output. I'll go ahead and open that. So the result was, you see it's a vec3, that means it's a 3D vector. So we have the X, Y, and Z coordinates of the center, components of the center of mass position. I happen to know that Y corresponds to the vertical. So I'll go ahead and plot the Y for the center of mass and the Y for the position of the right hand. Again, we want to plot as a function of time. I'll go ahead and add those curves. So in red, we see the center of mass position over time. We start at about 1 meter and change to 1.5. So it looks like, you know, the change in position from the start to the end was about 0.5 meter. And then the max height reached was almost 2.5 meters. And if we hover over, we see that, as we found when we were visualizing the motion, the max height occurs at a little after 1.6 seconds into the trial. So this is some kinematic analysis of the movement. With OpenSim, we can also look at the moments and forces involved in a movement. And to do that, we'll start with an inverse dynamics analysis next. So dynamics is the study of kinematics and the forces and moments that produce those kinematics. The purpose of inverse dynamics is to estimate the forces and moments that cause a particular motion. OpenSim determines these by forming and solving the model's equations of motion based on the model's kinematic structure and inertial properties, the joint angles that describe the motion, and external force data. In this tutorial, the inverse dynamics tool will analyze the joint angles from the inverse kinematics step that we just ran, and the external ground reaction force data from the experiment. And with the results, we'll be able to examine, for example, the coordination and timing of the sagittal joint moments to generate a max height jump. And we'll also look at whether we think the subject has a dominant limb driving the motion. So I'll go ahead and launch the inverse dynamics tool, and again, load a setup file. My inverse dynamics setup. And so again, The input is the inverse kinematics solution. I will use a low pass cutoff frequency of 6 Hertz to filter out high frequency noise in the IK results. Again, we'll process the same time range, put the results in a results folder. And now we have external loads. And this file specifies how to apply the ground reaction forces in our ground reaction force file to the model. In particular, we'll apply them, the forces and moments, to the right and left calcaneus of the model. So I'll go ahead and run inverse dynamics, and it's already done. And again, we have the same jumping motion. So now we can go ahead and look at the joint moments as well. So I'll bring up our trusty plot tool again, and this time plot the inverse dynamics results. And so I said earlier, we were curious about whether the subject has a dominant limb in the jump. So let's plot the, let's look at the right and left knee and right and left ankle flexion moments. Again, we'll plot as a function of time and add them to the curve. All right, and so if we look at the knee in red and green, we see the red, the ankle moment for the right knee is a little higher, and there's a more pronounced difference at the ankle. So these results would indicate that the subject may have a dominant right limb in jumping, but we'd probably want to collect some more data to be sure. So the power of OpenSim is that it includes muscle models, so we can probe the function of muscles in the motion. So while the motion of the model is completely defined by its positions, velocities, and accelerations, the distribution of muscle forces that drive the motion is not completely determined. This is because the model, for example, has more muscles than degrees of freedom. And so the static optimization tool solves this muscle redundancy problem at each time step by computing the muscle activations that generate the necessary joint torques and minimize the sum of squared muscle activations for all the muscles in the model. So in this demo, we will use static optimization to resolve the joint moments computed earlier using inverse dynamics into individual muscle activations and forces. And this will allow us to better understand the timing and recruitment of individual muscles in driving the max height jump. So let's go ahead and launch the static optimization tool. Again, I will load the setup file. I'll go ahead and start running it before I talk through, just because this analysis will take a little bit longer since it's more complex than the IK and ID we ran before. So again, we're analyzing the jumper model. Our motion is still the inverse kinematics solution, and we're using the same 6 Hertz low pass cutoff frequency. Our objective function to help resolve the muscle redundancy problem will minimize the sum of squared muscle activations, and we will choose to use the muscle's force length velocity relation when calculating the results. I'm analyzing every 2 steps to speed it up a little bit, same time range, same output. And here again, we're applying the same external loads. And we've also added what we call reserve and residual actuators. So these force generating elements can apply small forces and moments to each of the joints in the model and at the model's pelvis. And these can account for small inconsistencies, for example, between the model and the actual subject, or discrepancies between ground reaction forces and marker data due to experimental error. Or they can make up for the fact, so limitations in our model, like we don't have ligaments in this particular model. So we're seeing the model move, you saw the model move slowly, it looks like it's done now. And the individual muscles changing color from blue to red as they're activated. So we see the quads turning on during that counter movement, for example. And so since we're done, the static optimization problem has been solved for each time frame of the experimental data. So we can visualize and play back the motion. Again, sorry, it's a little bit jumpy over the webinar format, but you can see by the colors how the muscles are being used in the movement. And as for the other tools, we can also plot our results. So this time I will plot the muscle activations. So let me go ahead and make sure I'm loading the right file. So we saved the output of static optimization and results. I will plot the activations. And so let's look at gluteus maximus, the vasti, and gastroc. And again, I'll plot as a function of time and go ahead and add those to the curve. So previous studies have reported that maximum height jumping is coordinated from the proximal segments to the distal segments. In our data and model, we see that the recruitment of muscles seems to be consistent with this. So first we have the gluteus maximus in red, then the quadricep muscle, the vasti, which are shown in blue, and then the plantar flexors, the gastroc in green, are recruited. So our simplified simulation seems to agree with previous results. So this concludes the live demo that we'll do today. So I'll go ahead and close OpenSim. Well, I'll leave it open in case there's anything to show later and go back to our presentation. Before I do that, I'll make sure there are not any pressing questions. Okay, or technical difficulties. Okay, so let's switch back to, oops, our slides. Okay, so a quick recap of the demo that we did. So we got an overview of OpenSim's GUI. We then used the GUI to analyze motion capture data of a subject jumping with the inverse kinematics and dynamics tools in OpenSim's new output reporter. Then we used static optimization to solve for muscle activations that generate a jumping motion, and we saw how coordination moved from proximal to distal during the jump. So one question that you might be thinking and that you should ask about any simulation, is it good enough? For example, our model was simplified and we used static optimization, which in OpenSim doesn't incorporate tendon compliance. And so one thing we can do to gain confidence is to compare against experimental electromyography data. And here we see a reasonable match between the computed activations in black and the measured EMG in gray. But this is just the tip of the iceberg, and there are many other comparisons you should do to gain confidence in your simulations. For example, when running static optimization, I pointed out the residual and reserve actuators that we added to the model. You should look at the forces and moments generated by these components to make sure it is muscles and not these additional actuators that are dominating the movement. You can read our paper from 2015, which is cited here, for more discussion and recommendations. So to wrap up today, we'll show you how you can get the software and learn more about how to use OpenSim in your own research. So one way to learn more about OpenSim and its possibilities is by studying the work of others. The example I showed was just one pipeline and a few of the types of analyses you can do with OpenSim. There are many other possibilities. So next, I'll give a couple of examples of what some other researchers are doing with OpenSim. So as the first example, OpenSim is increasingly being used to analyze and aid the design of assistive devices. This example starts with a study that was led by Tom Michito while he was at Stanford. In a 2016 study, he began with muscle-driven simulations of running created by Sam Hamner, a former grad student in our lab. He used these simulations and OpenSim's computed muscle control to find the optimal torque patterns for an assistive device acting at the hip, knee, and ankle. And the goal was to reduce the sum of muscle activations squared by having these, while having these assistive devices. And Tom discovered several patterns in the torque curves predicted. For example, the optimal device profile didn't usually match the net joint moments generated by muscles. So now switching to the right-hand side, Euclid and his colleagues at Harvard used the discoveries from Tom's simulation study to help design an assistive suit for running. So the suit-assisted hip extension, the bar plot shows the results, and the key comparison is the blue versus red bars. The suit that used a torque profile based on the simulation results led to a significantly greater reduction in metabolic rate compared to a torque profile that was just a scaled version of the biological moment. So the simulation results improve the performance of the assistive device. And this is without extensive and expensive human experiments and device iteration. So we see this as a big opportunity for biomechanics, in particular simulation-based design of assistive devices for running, walking, and also pathological gait. Researchers are also using OpenSim to answer clinical questions. So one of these researchers is Marjolein van der Kroot. She's a former visiting scholar and pilot project awardee with the National Center for Simulation and Rehab Research. So cerebral palsy is a neurological disorder that leads to a wide range of gait pathologies. One contributor to gait pathology is the muscle spasticity that's present in children with CP. Marjolein's research question was highly clinical. The end goal is to understand how muscle spasticity affects muscle function during walking in children with CP. As a first step, they modeled spasticity in OpenSim. They also developed experiments to measure spasticity. And in order to accurately simulate the experiments, they extended OpenSim to include a spasticity controller. Then they compared the forward simulations with spasticity, that modeled spasticity, to experimental results from their instrumented spasticity test. And then next, the researchers are incorporating this spasticity controller into simulations to understand how muscle spasticity affects muscle function during walking. And it's not just humans. OpenSim is also being used to simulate and analyze animal movement. So Jeff Rankin and colleagues at the Royal Veterinary College created a model of the ostrich lower limb. The researchers generated simulations of running, shown in green, and walking, shown in yellow in the plot, using the computed muscle control tool in OpenSim. For each muscle group, they computed the negative and positive work performed by the muscles during stance and swing, where negative works on the left, positives on the right. This plot shows the results just for the stance phase. The biarticular muscles crossing both the hip and knee perform largely positive work during stance, contributing to propulsion, while the knee extensors performed negative work, shown here, acting as brakes. So these are just a couple of examples. OpenSim is being used for many other purposes, for example, to study injury mechanisms or to simulate upper extremity motion. It's always really exciting to see the many other uses of OpenSim featured in publications. So we provide a wide range of resources to help researchers get started with OpenSim. We have extensive online documentation, and this page shows the main portal to documentation and support, and I'll walk through some of the main sections. So we have this Getting Started section, which includes a link to download the software, a guide to new features, a guide to how to install the software. One of the places it links is to simtk.org, and this is where we post and share the actual software download. We also share our source code via GitHub. We welcome others, including you, to contribute their models or contribute to the code, for example, by helping us fix bugs. So we have our documentation. So we have a user's guide for users getting started primarily with the GUI. We have a guide for and documentation for individuals using scripting through MATLAB or Python, or developing in C++. We have links to key theory and publications, and then we have the Doxygen, which is additional documentation for developers. We provide a number of examples and tutorials ranging from introductory tutorials if you're just getting started to more advanced tutorials that use MATLAB scripting and C++. We have troubleshooting, so the forum, which I'll show you a little bit more about on the next slide. We have best practices, which includes a link to the validation and verification paper I mentioned earlier, and other best practices from our lab and others, as well as frequently asked questions. For troubleshooting, the forum is a great resource, so you can get help from the Stanford OpenSim team and also the rest of the OpenSim community. And I want to thank anyone in the audience who's already asking and also helping us to answer questions as well, because we really do want this to be a community resource. So you don't have to start from scratch. We also provide links to existing models, data, and tools, models, data, and tools developed by our lab and elsewhere. And then we also have our teaching hub, which links to the OpenSim YouTube page, and then pages from past courses and workshops. For example, here's the YouTube page, which hosts videos from past webinars that the NCSRR has run, galleries of examples, and more. If you want to learn more about the software, you can also check out our recent publication in PLOS Computational Biology as well. To close, before we switch to questions, I want to acknowledge the huge team of contributors that make OpenSim possible. Some of the key contributors to OpenSim 4.0 from Stanford are shown on this slide. Thank you to them, and thank you to everyone who gave us feedback and helped with beta testing of the software. It was a true team and community effort. OpenSim has been supported by a wide range of grants, with a big portion coming from the National Institutes of Health in the US, which funds our National Center for Simulation and Rehab Research. And with that, I want to thank you all for joining and being flexible and switching the hosting platform. And with that, I will go ahead and switch to answering questions. Let's see. So if you have questions, I know there's both a chat interface and a Q&A interface. I'm going to go ahead, just to simplify, I will look at the Q&A interface. So if you have a question, please answer it in the Q&A, or please ask it in the Q&A. So I can more easily keep track. All right, so there's a question from Carlos Concalves. Apologies if I have mispronounced it. Is it possible to convert C3D data with the OpenSim GUI to MOT and TRC files without MATLAB? So you can read those in, but getting them into the, so you could read them in and plot them, but to get them into to do the pre-processing and cleanup steps, you generally do need to use MATLAB, or the other option, if you don't have MATLAB, is Python, which can help. In the future, we hope to add more tools to directly support the manipulations that you need to do in the GUI. Another question, this is from Joseph Garrett Sullivan. So recent work from Brian Umberger and Frank Supp has demonstrated promising predictive simulations for walking with assistive devices, but their work relied on using direct co-location methods. Are co-location methods featured or supported in OpenSim? If not, is support for co-location methods planned? And so this is already in the works and should be available more widely soon. So we had a workshop at ISB, if anyone was there. So it's called OpenSim MoCo, and it has direct co-location methods using OpenSim models, examples, and documentation, and that should be out sometime this year, hopefully. At least an initial beta version that others can use. So keep an eye out for that. Um, so, so a question from Lex, am I seeing it correctly that you can change the exponent for the static optimization objective function? And yes, you can do that. You can just change the exponent. The benefit of the OpenSim MoCo, which I was talking about, is that it does support even more flexible and varied optimization functions. So that will be something to look out for. So a question from Viswananth. When I tried OpenSim first, I need to import the model and then we need to scale, but I didn't see you scale. I did the scaling ahead of time. Scaling is really important, as I mentioned, to get a good scaled version of your model, particularly if you're doing inverse dynamics and muscle generated simulations, but it does typically take some time and iteration to get a good scaled model, which is why I did it ahead of time. In the NCSRR webinar series, we did a webinar just about scaling, and you can find that on the NCSRR YouTube page to learn more about the process of scaling, and also in our user's guide. Let's see. So there's a question, could you briefly describe the difference between using static optimization or RRA and computed muscle control, and why I chose static optimization for the demo? So static optimization is solving statically at each time step is one difference. So I couldn't use the activations to drive a forward simulation, whereas computed muscle control will allow you to do that. Computed muscle control also allows you to incorporate tendon compliance, which might be important, for example, if you have a higher speed movement like running. As far as RRA, this is a good thing to bring up, is so what the RRA step is to help reduce the residuals that are applied by making small adjustments to the model and the inverse kinematics to essentially help F equal MA. We need to have F equal MA, and there'll be small differences, as I mentioned, between the model and your actual subject, or some error in your experimental forces versus marker data. And so with the RRA, we can try to reduce, as I said, some of those residual forces that are applied. And it's actually usually helpful to do that before running static optimizations when you're running simulations that you're going to use in research. So let's see, other questions. Apologies, I'm sorting and reading through these. So there are some questions that I'm seeing just about getting started. So places to get started are generally looking at, we have tutorials 1, 2, and 3 under the introductory examples, and reading through the user guide as well. Another thing that can be helpful is to look at the NCSRR webinar series if there is research that is similar to the type of research that you want to do. To check those out. Another exciting thing that's happening is that since there are a growing number of experts outside of Stanford in using OpenSim, some of those researchers are starting to run introductory tutorials in different locations. Like, for example, Ilse Yonkers and Friedel de Groot have run, and others have run some OpenSim tutorials in Europe for the past few years as well. Let's see. So there's a question about marker sets. So you can change the details of the marker set to match your own. So you can change these, the names, for example, these markers and how many there are in either associated with your model to customize to your own setup. So there was a question on the forces file, so I could go ahead and bring that up and show a little bit more detail. Oops, let me go ahead and load the inverse dynamics setup file. So here's the file. I had already pre-created it, but you can also create it on your own. So you can have, so in this case we have, and this is often the case in GATE, we have a right and left ground reaction force. The forces data is in this jumpforces.mot file. And for each of the force, you can specify the body that the force should be applied to, whether it applies force and or torques, what reference system the forces are expressed in. And these drop downs are just specifying the name, like which name in the file, which column in the file corresponds to XYZ. So that's the, and there's more detail in the user's guide as well. So we're getting pretty close to 10. I know we started a little late, so I'll take a couple extra questions. And then if there are questions that I don't get to, I will either, we can send out a link to our FAQ section if the question is already addressed there, or can add it if it's not already readily available in the FAQ. Let's see. There's a question about IMU-based motion capture, and that's something else that is in development and we hope to share soon, so keep an eye out for that. There's a question about which programming languages are needed. If you're able to just use the tools that are available in the GUI, you don't need to know programming. If you're trying to do something that isn't readily available in the GUI, there's a lot you can do with MATLAB or Python scripting. Or if it's, if you're trying to, for example, create a new kind of muscle model, then you'd probably need to program in C++. There's a question about accounting for, so static optimization models tendons as rigid. That's only true for the static optimization analysis. If you're generating forward simulations or using the computed muscle control, it does include compliance of tendons. I'll go ahead and answer one more question before we go ahead and wrap up. So how can we perform a what-if study for simulating a perturbation or extreme loadings? And for doing those kinds of extreme perturbations, that's typically the case where you need to move to a predictive simulation where you're potentially generating a completely new movement. And so if you want to learn more about the process for that, Thomas Geitenbeek is a researcher in the Netherlands, and he's actually giving a webinar as part of our NCSRR webinar series, where he'll talk about a platform called SCONE, which is designed to aid the process of generating predictive simulations where you're not directly trying to follow measured experimental motion capture data. So that should be a fun webinar. That's actually next week. on Thursday. So you can see that on the OpenSim webpage to register for that as well. So since we're getting past 10 o'clock, I'm going to go ahead and wrap up the webinar. Thank you again to everyone who joined. I will look through the questions and add them to the FAQ if they're not there, and make sure that we get a link on the YouTube page, or perhaps Hassan could email out a follow-up email as well. So thank you again to everyone for joining, and we'll hope to see you again at another webinar, at a conference or OpenSim workshop, and thank you again. Bye, everyone.